Optimization problems with Elijah and Nick Matzik. Optimization problems are used to find the most suitable maximum and minimum when working with a problem. The first example, find two positive numbers whose product is 225 and whose sum is a minimum. The first step, interpretation. What are they asking? What is the number with the product of 225, and when is the sum of those two numbers a minimum? The first step is to make an equation. So this is the equation that you would use, seeing as neither one of the bases is altered. X times y equals 225. And they're equal, no coefficients. And the standard equation that you are given is S, which is the sum, equals x plus y. The next step, step 3, is to set the equations equal to each other. So you rewrite this equation, x times y equals 225, to equal y equals 225 over x, and plug it into the original equation that you were given, the sum. And once you do that, you can substitute the y in this equation for this one. And so you are given this overall equation right here. Once you've done that, you can multiply by x over x, or also known as 1, and you can make your equation more suitable and easier to use, clean it up. And after that, you find the derivative of the equation that you just found. So by using the quotient rule there, you can find the derivative of your equation and clean it up, and you're almost done. Step 5 is to set the equations equal to 0. Well, really just the top. And so it's x squared e minus 225 equals 0. And so once you do that, you can find that x squared equals 225 and that x equals 15. And that is the positive number where the product is 225 and the sum is a minimum. And you are done. Example 2, fence optimization. In this example, we have 2,400 feet of fencing that is used to enclose a rectangular field which is bordering a river, shown below. The first step is to draw it. It's your interpretation. And so this is the 2,400 feet, and there's your river. And next you write an equation stating what you see in your drawing. So this is 2x plus y equals 2,400. And also you have your given equation for area, which is x times y. Next, you substitute your original equation, and so once you do that, you have to rewrite it so that it's in xy, or it's in y format, and then you substitute your equation that you just made into your area equation, and you get area equals x in parentheses 2,400 minus 2x, and you rewrite it and clean it up to make it 2,400x equals, or 200,400 area equals 2,400x minus 2x squared. Step 4, you find the derivative. So the derivative of the area equation would be area derivative 2,400 minus 4x. And you solve for that by setting it equal to 0 and realizing that x equals 600 by dividing through by -4. And after you find that, then all you have to do is test it. And when you test it, you can plug in different values and see that this 600, the x that you just found, will give you the optimal area because the other ones are just 0. And then you rewrite your answer by saying, therefore, that area which you just solved is the best choice when using the closed interval method for finding your optimal fence area.
Example 3, optimization with a three-dimensional object, in this case a cylinder. Now with this problem that you are given a set of text which can be easily translated into find the minimum surface area while the volume is 2,000 cubic centimeters. Right here you have a fairly simple 3D drawing of the object, as well as the two equations that you start with. The volume, which is 2,000, equals pi r squared times height, and the equation for the surface area. Now to start with, you change the volume equation to solve for h, which will give you h equals 2,000 divided by pi r squared. And then you input that into the area equation, as seen right here. And in that case, it cancels out parts in the denominator as well as the numerator, which will turn this portion into 4,000 over r plus 2 pi r squared, which when you rewrite it will look like this, simply to make it easier to find the derivative, like this. And again, optimizing it. After this, you have to set the bases equal, which means you multiply by this 1 by r squared, which will give you the equation a prime equals 4 pi r cubed minus 4,000 over r squared. Now, your value for r cannot equal 0, so you discount the denominator, which will give you a prime equals 4 pi r cubed minus 4,000. Set it equal to 0. Simplify, solve for r. And r will equal 6.828 centimeters. When you have the r value, you input the r into the earlier equation where you solve for h, which will give you 13.656 centimeters. So your final answer will be r equals 6.828 centimeters, and the height will equal 13.656 centimeters.